As mentioned, my name's Long. I work at Sienna on the analytics team. So it's like the big data machine learning team. And I'm here to talk to you guys about Spark 2. How many of you guys would consider yourselves like Spark beginners? Okay. Scala? Okay. So all the code you're going to see is Spark in Scala. So it'll be fun. So what's Spark? We always sort of begin with this picture. Spark is like a general computing big data framework, right? So that's kind of what's at the bottom here. We call that library Spark Core. And on top of this general computing framework, we have 4 specialized libraries. Graph processing, machine learning, streaming, and SQL. And SQL is like structured data, any data that can be represented in like a tabular format. Oh, before I keep going, when I practiced this last night, it took 90 minutes, so I might skip some slides. Unless you guys really want 90 minutes of this. So the main thing that makes Spark work is called an RDD, which is a resilient distributed data set. So you can think of RDDs as like a parallel collection, right? Except you can parallelize over 8,000 machines. Sometimes people say 10,000, but maybe not. And it's resilient in that if one of your 8,000 machines goes down, it can resume that work either on that machine when it comes back up or somewhere else.
So the data set, like this object, consists of like the actual data stored on a bunch of machines and the kind of protocol to evaluate.
Kinda. I'll keep going. Okay. And I explain it a little bit. Okay. On AWS, the failure rate is something like 2%, right? If your 1 out of 8,000 machine goes down, you don't necessarily want to restart the whole job on all 8,000 machines. You want that one machine that's failed to come back up. So how does it work? So RDDs, right, which are your collections, are immutable. So every time you do a transformation, like you say string to uppercase, it actually gives you a new RDD back. And what actually happens is that it's not executing that to uppercase. It's appending to a graph of computation, and it's saying, and as you're building up your series of transformations, it's making this graph, and it doesn't do anything until you call an action. Like an action would be like print line, write to disk, count. Right, so this concept of building up your graph of RDDs is called lineage. And so when a node goes down, your RDDs remember their lineage. So they can go all the way back to source on a particular node and rebuild that graph of transformations. That's kind of how the resiliency works. In the big data world, word count is our hello world, right? So you have a text file, you want to count all the number of times a word has happened, and that's okay for text files. But if you like wanted all of the negative tweets Donald Trump has tweeted, maybe that'll blow up your computer, and you don't have enough memory for that. So you need like a big data solution. So in Scala, word count's really easy. It's so I have like, this is a string. I say 2 lowercase. I split on space. So this is like a really naive solution, right? Like we could split on apostrophes, quotes, whatever. And I have this function group by, and I'm just saying group by myself. So it's going to return me back a key value pair of each word, and then an array of like every time the word happens. Right, so now I have a key value pair of a string and an array, and I can map over values. So map over values is take the values of my key value pair and apply this function, right? So it's a higher order function. So I'm just going to say, give me the length of my array. So this is going to return me a key key value pairs of words and the number of times that word happens. So at Spark, it's extremely similar. So that's kind of why we always say if you want to learn some Spark, Scala is a good thing to learn in parallel. So to get into Spark, the entry point is called a Spark context. So you instantiate a new Spark context. And then these are, it's mostly the same, right? It's the same code, except words here. The Spark context will actually give me an RDD of strings, whereas this was just a one long string. So here I'm mapping into each element of my RDD, and there's a string inside it. I have a flat map because I split on space, so each element of RDD is going to give me an array now. So I flat mapped it to that. It's a one-dimensional RDD instead. And then these two are the same here. So this is the directed acyclic graph of computation of word count. So as you build RDDs, it's continuously appending to this graph. So we'll go over this really quickly. There's a streaming library in Spark called Spark Streaming, and it's built on top of RDDs. And it's not pure streaming, it's like micro batches. So it does like half a second of work at a time, or like 10 minutes of work at a time, depending on what you tell it to. And most streaming operations, you'll do some sort of window-based operations. So if you think about Twitter, for a trending, you see that list of trending tweets, right? So they say, the last hour, these hashtags are trending. So that would be your window. That'd be like an hour-long window. But how often do they update this this list of tweets, hashtags? So the frequency that they update is called the slide. Right? So here, if this was an hour, we're sliding 40 minutes at a time. And then because Spark streaming is in micro batches, you have these intervals, these half-second in micro batches that you have to slide a multiple of. It sounds complicated. It is complicated. It's a headache for everyone. So that's word count in the streaming library. This is what we really want to talk about, is data frames. So data frames is the library for structured data, right? So your JSONs, your CSVs, your SQL, your Parquet files, anything that can be represented in rows and columns. And SQL is the library, data frames is the abstraction. So this is some data frame code. So this is word count with data frames and word count with SQL. So data frames, you can manipulate them like collections, except instead of map, we do .select. This is the same as before. We have a Spark context, we get a text file, but then we say to data frame. And we're not dealing with objects in this case, we're dealing with columns, right? So the name of the column is line. And then I have a data frame of string. And I do select, which is my higher order function. And there's a split here, right? And then explode is like a funny name for a function that takes, after you split, it creates a bunch of new columns, and explode takes those new columns and turns them into rows. And then I do a group by an account. And so that's word count in data frames. And then there's the SQL version, right? So in the SQL library, you can write SQL. So it's really cool and incredibly painful. I don't suggest trying it.
Unless you got SQL.
Yeah. So the SQL library isn't just two confusing new ways of writing word count. There's a lot of cool stuff that happens underneath. So one is called Catalyst. So every SQL engine has a query optimizer, right? So you can write kind of really suboptimal SQL code, and it'll optimize it for you. So for example, if I had a table of students and a table of classes, and I wanted to know which students have taken CS 100. I might do students, join classes, an ID, filter by class CS 100, and then give me everyone's last names and the class name. If I executed it that way, it would suck because the student table could be humongous, the class table could be humongous, and if I do a join, it's a multiplier, right? It's exponentially bigger. So query optimizers essentially work it so that it minimizes the amount of data it has to deal with at any time. So Catalyst is the query optimizer in data frames, and it does three basic things. So the analysis portion basically goes through this and makes sure that line df is a real table, line is a real column, word is a real column, right? It just goes through your SQL and makes sure that what you've written actually exists. And once it's resolved all your references, it creates a logical plan. And next part is the logical optimizer. The logical optimizer is where all the fun stuff happens. So there's basically something like 100 rules that get applied to your logical plan. So when we talked about students and classes, we want to filter the classes before we select the whole table, right? The rule that works that is called predicate pushdown. So push the predicates as far up your RDDs as possible. And then I said, I only want my student names and my class ID. It doesn't make sense really to have all the columns to do my joins and my filters, right? I just need these 2 or 3 columns. So the rule that takes care of that is called column projection. So those are two, right? There's Boolean simplification. There's again like there's 100 that get walked through the AST. So once all the logical rules have been applied, the third set of rules that get applied is the physical planning. So you have to remember that we're operating on 8,000 machines. So the physical plan tries to determine where is the best machine to put what data. So there's not that many rules here. There's, I think, a dozen rules that kind of get applied. And it's non-deterministic, so it creates several plans that get put through a cost model, and then they select the best one selected, and then at the end it generates RDDs. So it's all RDDs at the bottom. So the second really cool thing about data frames is Project Tungsten. Project Tungsten, to motivate it a little bit, in 2009, when Spark came out, we ended racism, right? We elected Barack Obama. But our computers were disk-based hard drives. We had like 10 gigahertz network speeds. We had 3 gigahertz CPUs. But 8 years later, we're ending sexism. We have solid-state drives. We have 100 gigabit network speeds, but we still have 3 gigahertz CPUs. Sometimes.
44.
So in 8 years, like a lot has happened except in the CPU space. So Project Tungsten is a bunch of very low-level optimizations in Spark. It's ongoing. It's not like finished, and it'll probably never be finished. But so I can give you some examples of what happens in Tungsten. So for example, strings take up a lot of space on JVM. And if you have a billion strings, that's a lot of extra overhead on JVM. And not just memory-wise, but if you have to serialize strings between machines or any sort of objects between machines, this takes up a lot of processing time as well as memory. So in Spark, there's something called UTF-8 string, which is actually stored off heap, and it gets rid of all the extra JVM overhead. And because Spark is managing this string, this binary string representation, it actually also manages the memory. So you remember Catalyst tells you exactly when and where something will be needed. Spark knows exactly when to garbage collect any of the binary data that it's taking care of. And then there's like 3 general categories of optimizations. And the third one is cache-aware computation. And just like waiting for a hard drive sometimes slows our processes in memory, the L1, the L2 cache are sometimes slowed by dereferencing pointers, right? So Spark has basically a cache, well, one of the things that it has is a cache-aware binary map, where in a key-value pair, the keys are actually stored in cache, so that any sorting operation, for example, can be done in cache instead of dereferencing pointers to memory. So what this gives us in general is that data frames are much faster than RDDs, and in the 4 supported languages, data frames have an equal performance, but in RDDs there's variations. So now that we know about data frames, we can talk about structured streaming a little bit. So 2.0 came out at the beginning of August, and it's the alpha release. So the way Spark usually releases libraries is that they'll release just like the thinnest possible API to get you from A to B, or A through Z, with very little functionality, except to just try it out and do one thing with it. So 2.0 was the alpha release of structured streaming. The only thing you can do really is read a stream from console or text file and output it to console or text file. So this is, I call it classic streaming, but when we think of streaming, we get some data, we do something to it, we dump it into a database, Kafka, and then we let other applications pick that up and do whatever they want to do with it. But what is increasingly common is that we have this stream of data, right? We continue doing our manipulation of some sort, we dump it into a database, but we also hook up like data science notebooks, like Jupyter Notebook, and we want to query our stream and see what's happening. We have dashboard applications, right, so that somebody's monitoring the status of our stream of data. And kind of what everybody really wants is to have machine learning models that can take new data and learn on the new data instead of having to relearn on the whole batch, which might take days, right? So this sort of stuff people build all the time, but it's a lot of work and a lot of scaffolding. And the idea behind structured streaming is that structured streaming will eventually be able to do all of this with just one API. So it's a simple idea, but it's kind of cool. The way to think about structured streaming is to think of incoming data as an infinitely growing table. Right? So all the new data comes in basically just counts as new rows in a data frame. So in our word count example, we have new words coming in, and you can see that every set of input is a new row. We do a word count, and it gets output to some sort of result table that we can output to console or file for now. So this is the code. So in Spark 2, we don't have an SQL context or a streaming context anymore. We have a Spark session, and the Spark session lets us basically read in data. So there's like a bunch of reading functions and writing functions. And this is our word count in 2 lines. So a lot is happening here. This could be a batch job or a streaming job. Like at work, we're like, for new projects, people are always like, should we start writing a batch solution or a streaming solution? And it's always like, like it's these 2 different technologies that don't work well together, and they each have their own separate considerations, and your client might want one thing over another. But with this, the idea is that you just write the same piece of code, and it can be a streaming job or a batch job. So if this was a batch job, the only difference would be like I'd remove stream and I'd remove stream. It would work as a batch job. So that's amazing. Another thing that you think about in streaming sometimes is reliability, right? Like, so the stream's going to go down. What are we going to do? How do we recover? What's the best method? And there's a ton going on underneath to make sure that we have some reliability in our streams. So there's an exactly once guarantee in structured streaming. So if you think about delivery the term is delivery semantics. So there's 3 major delivery semantics. At most once, right? So at most once guarantees means that I send you a letter, you're going to get it once or not at all. And then there's at least once guarantees, where I send you a message and you'll get it once or 100 times, but not 0. And then those are easy to implement, but exactly once is hard, right? Like I send you a message and you have to, you're guaranteed to get it. If you've turned off your phone and turn it back on and get the 10 similar text messages from the same needy girl on Tinder, it's not always that she's the needy girl on Tinder. It's because delivery semantics are hard. So hard that like our cell phone carriers haven't really solved that yet either. So so how do we propose to have exactly once semantics? So there's a few ways that streaming applications can fail, right? So I get a bunch of messages and I'm doing a word count, let's say. And as I'm counting the words, I die. But I want to have this, I want those words counted. Like, I want to reliably still have those words count. I don't want to come back up and just skip over them. So one of the things that happens is that we have a planner. This is basically Catalyst. So Catalyst is our query planner, but in the structured streaming world, it gives us what's called an incremental plan. So it'll plan just the 5 seconds of data, right? So when I have this plan from Catalyst, it gets backed up to a write-ahead log on HDFS. So if I die in the middle of processing my current plan, I go back and I'll know exactly what it was I was doing at the moment of I died. So I have a word count, right? It's been an hour. I know how many words are around. When I come back, when the system comes back to life, it still needs to know what the last word count was to keep adding to it. And so that's our state. So state is stored in, it's always silly to say this, in the state store API. So there's only one implementation so far, and it's Delta files on HDFS. But I'm sure somebody will implement more interesting things. So when I come back to life, I get my plan from the write-ahead log, and I get my state from the state store API, and I can resume what I was doing. But if but I get my plan, and the source of tweets has kept going, right? How do I go back and get those tweets again? So there's a restriction on sources that they have to be replayable. So anybody that implements a structured streaming source has to have this concept that I can scroll back and get the last X batches, let's say.
So in the middle, like things can happen more than once, but if you have side affecting operations or something.
You didn't like your question.
I think that happened in the middle.
Sorry, say that again?
So it's exactly once, like means the sync will only get it once.
Right.
Once and only once, but the stuff in the middle can happen more than once. Like if you have a side effect like printing or something, that can happen more than once.
Well, yeah, I guess if you're printing to like console, that would happen once.
Yeah, or anything.
Yeah.
Text message.
Yeah. So the last part is syncs. So syncs could be a console or like Kafka or Cassandra, and the restriction on syncs is that they have to be. The word is idempotent, and in math, idempotent means like if you times it by 1, it should be itself. But in streaming, idempotent means if you have 100 of the same messages or 1 of the same message, you have to be able to reproduce the same result.
The sync needs to be idempotent.
Yeah.
So then you don't actually have it. Like your sync gives you end to end.
Yeah, the sync and the source do it, essentially. So the APIs have to implement these idempotence and replayability, or else the system fails.
Yeah, the middle part needs to be able to restart the replay, and it needs to check the sync that it's right.
The source gives you at least once, the sync gives you.
Yeah. And the middle part gives you the ability to restart after failure.
Right.
Right.
So so I guess the implementation has to exist in the source and the syncs for this to work. It's not, Spark isn't going to do it all on its own. It's the replayability has to be implemented in the Kafka API, right, which is an obvious one. So that's it. In conclusion, structured streaming, right? You get data frames, you get Catalyst, you get Tungsten. You only have to write sort of one code to get batch and streams, which is probably the biggest part to me, because we like the last 2 projects, it's like, where do we start? And then you get exactly once guarantees. And then, so I mentioned it's kind of the alpha release. 2.1 should be like end of November, and what's kind of in scope for 2.1 is Kafka integration. The API for sources and syncs is currently not public, so those should be in 2.1. Watermarks. So like we said, these are infinitely growing tables, which is not feasible, right? So watermarks is a way to say I no longer need a certain X amount of data. And ML integration. So right now, k-means I think is the only machine learning algorithm that can take in new data and adjust. The idea is that all the machine learning algorithms will eventually be able to train on new data. And I always have to say, the mark of a good presentation is gaining Twitter followers. So Twitter and GitHub is a long Tran with 5 O's. And if you get the slides, there's like a dozen sources for this talk.
The slides on GitHub.
Yeah. Thank you.
You mentioned at one point that there's a performance difference between you had a slide